Hi, what we're going to do is review section 11.1 and 11.2, which is really just analyzing a bunch of characteristics about graphs and different types of regressions. So between linear, exponential, and quadratic regressions, we're going to write equations and talk about domain range, minimum, maximum values, and then we'll make some predictions too. So I'll get started on this first problem, which depicts the price of a stamp from the year 1920 all the way to 2005. So it's just taking a cluster of data points really and over that range of time. Looks like there's no specific interval. Looks like there's like no data for the 1940s, and then all of a sudden there's a bunch of data after 1960. So it looks like it's an exponential curve. So again, it's kind of has the data itself without the line going through it, has a bunch of just points that start really low, and then there's a smooth curve up. So there's an exponential regression that's drawn through, which of course is going to keep going to the left, and the regression is going to keep going up and to the right. So when we identify domain and range, we'll do it in context of the data set and in context of the problem. So when I say the data set, I'm talking about specifically these points that are up here, and then when I talk about the problem, we'll talk about the fact that like time is independent, so it's going to keep going infinite in both directions. So first thing we'll discuss is domain values, which are the x values. So according to the data set, the lowest actual data value that we have is in the year 1920. So you would say 1920 is less than or equal to x, is less than or equal to the highest point that we have, which it looks like if you take this point all the way here and you draw it straight down, it looks like it goes through about 2005. So according to the data set, the actual domain is from 1920 all the way to 2005. Notice that even though it's discrete, it looks like, as far as just having points, the time itself is continuous. At any point from 1920 to 2005, according to our graph, you can just basically go into a post office and buy a stamp. So the data itself is continuous. In terms of the problem situation, notice we started collecting data in 1920, but stamps were around before that, and obviously stamps are still being produced. So we're going to say that our data is all real numbers. According to that curve, the data is all real numbers. There was probably some point when stamps were starting to be produced. If that was 1900, then that would be our low value. But again, we're assuming that time is going to keep going in the positive direction to the right. So that's why the domain would keep going infinitely in the positive direction. The range values, according to the data set, the lowest price of a stamp, this is measured in cents, this lowest value right here looks like it could be around 2 cents. So I would say we're going to say 2 is less than or equal to y is less than or equal to as much as it is up here, which it looks like it's around 39 cents. So the range, again, of the data set itself is going from 2 to 39, but realistically the price of a stamp could be all the way down to 0, and you could just have free stamps, and we could keep this curve going in this direction up here, which means it's going to keep getting higher and higher, and the price of a stamp is above 40 cents right now, so it is going to keep increasing. So for the sake of that, we're going to say that y is greater than or equal to 0, which means you could technically get a stamp for 0 cents. You could also end up paying eventually $5 for a stamp. Who knows? So in context of the problem, we're really saying let's just look at the big picture. You can't have a negative price, so that's why I'm not going to say all real numbers. It's because you can't have a negative price. But I would say it's greater than or equal to 0, just to establish the fact that 0 does mean like a free stamp. The next one, is there an absolute minimum or maximum? Explain. You would say really according to the data and this graph, there is no minimum and maximum, but in context of the problem, so I'm going to write that here, in context of the problem, the absolute minimum, and that would be whatever the lowest price of a stamp would be, and like I had said, the absolute minimum is 0 cents. So you cannot have negative cents. So I would say that we have an absolute minimum of 0 cents, even though what we're really talking about with absolute minimum is when we end up with the U shape, the absolute minimum is going to be this bottom point. So in terms of this curve, it really is going to keep, if you think about it, before 1920, they were even cheaper and cheaper and cheaper. But again, we're establishing that it is still a positive number or something that is equal to 0. And then the last problem here, which says what is the price of a stamp in 1990 according to the data. and then does it match the regression equation? So I want a side-by-side prediction, and I want to know exactly what it was in 1990. So I'm going to put my cursor right between 1980 and 2000. So 1990 would be exactly where my cursor is. According to the data set, I'm going to assume that it's this point right here, which looks like it would be about 29 cents. So I'm going to say according to the data, the price of a stamp in 1990 was 29 cents. Now, the regression equation is different than that. If I still go to where 1990 is and I go straight up, notice that that point on my curve is actually around 23 to 24 cents. So I'm going to say the regression equation has an approximate value of 24 cents. So it's close. It doesn't obviously match it because the regression equation is just a prediction. So since our range of data for what I have in blue here is from 1920 to 2005, 1990 is within that range. So this is what we would call an interpolation, and I'm going to kind of just write that right next to this down here so you know the key term. This is interpolation because it is a prediction that is within our set of x values. So it's somewhere between here and here on this line. So we are able to predict and compare it to our actual data number. Next problem. So I really enjoy this one too. You guys probably heard the word fuel economy before, talking about how many miles per gallon a vehicle gets. And usually when you see an advertisement for a car, they'll tell you how much it gets on the highway versus how much it gets when you're driving in the city. And that's because your speed in the city is obviously a lot lower and your speed on the highway is a lot faster. But what you see is when you hit really high speeds, what happens is your fuel economy actually goes down and you are burning a lot of fuel excessively. What happens at the really low speeds is when you start and stop up your car, you're also having low efficiency. So really there's going to be a maximum fuel efficiency in terms of this problem situation, but we'll just go through and identify these questions again just like we have. So determine the domain and range of the function. So I'm specifically just going to refer to my actual function outside of my data set. The domain that it looks like, I would say is x is greater than or equal to 0. Notice that we're not really going to identify that we have a maximum speed on the car. We cannot go a minimum speed, but we know for a fact that we can drive faster than 80 miles per hour. So I'm going to say safely that our speed of our car is what our x quantity is, and it is going to be greater than or equal to 0. The range values. Notice that we hit this point up here at the very tippy top of the graph. We are going to call that a maximum value, and we know that our y's are never going to get higher than that value. So our y's, the fuel economy, are never going to be above that value, and they're never going to be below 0. So I'm going to say 0 is less than or equal to y is less than or equal to 31. So again, you know that this parabola is going to keep going down, and you cannot have a negative fuel efficiency in miles per gallon. So that's why in both of these cases we would say that your fuel efficiency would technically be 0 if you kept the curve going. But in terms of our problem situation, the maximum that we have is going to be 31 miles to the gallon. Identify what the absolute maximum is. So that's what problem 2 is saying. So the absolute maximum is 31 miles per gallon, which represents the highest fuel economy. So again, we're talking about the fact that this car, while it was driving, hit a top speed, hit a top fuel efficiency, which was around 30 miles per gallon. So as this car was driving and kept increasing speed, the fuel economy was increasing, then it hit a certain point, and then it started decreasing. And that's what this next part is really asking, is identifying intervals of increase and decrease. So what it means by that is I want to know from when this car started driving to when it peaked out, was it increasing? So it looks like the car had to have started at 0 miles per hour. So I'm going to say it's increasing the fuel economy was increasing from, and I'm going to say from 0 all the way up to where this highest point was, which if I keep my cursor going down, I would say this is probably about 41 miles per hour. So I'm going to say increasing from 0 to 41 miles per hour. And it looks like what happens is right after you hit that 40 miles per hour mark, your fuel efficiency starts decreasing. So I'm going to say it's decreasing from 41 to, and it looks like all the way down to about 80 miles per hour. And that's as far as the data is concerned. Again, I'm just looking at that curve. If you extrapolate the data in both directions, which means if I do keep this curve going here and I keep it going in the other direction, you are extrapolating data, and it's going all the way down to the x-axis, which is where we said we assume that the fuel economy could be 0. And notice that it's at this speed where he's starting up the car, and then it's all the way at 80. And then the last one, what we're going to do for this problem is enter a bunch of data in, which really relates to my life. I'm a coffee addict, it's bad. And we're talking about the temperature of a cup of coffee as it's poured. So we're going to graph the data set on the coordinate grid and enter it in the calculator, get a regression equation, and make a prediction. So on the x-axis, I'm going to label that this is going to be time measured in minutes. And this would be the temperature of my coffee. And we are doing this all in degrees Fahrenheit. So across my x-axis here, I'm going to count by 5s. And notice the time goes all the way up to 50 minutes on where the data is collected. So I'm going to keep this going. So it's from 0 all the way to 65 minutes. And then on the y-axis, we can start as low as what this minimum is here. I'm going to say that my minimum temperature, I'll just set and put a little squiggly on my graph, which indicates that I'm jumping from 0 to whatever this next number is. And I will start it at 50 degrees, we'll say. And I want to go all the way up to 180. So I think I can count by 20s. Let's see if that works. So 70, this would be 90, 110, 130, 150, and I'm going to put 170 right here. So it's going to start up there. I'm going to actually put 190 up here so we can be a little bit above. And what we're going to see is a curve coming straight down. So I'll start making my points. So at 0, I'm at 179.5, so it's somewhere around here. At 5 degrees, I'm at 168. 8 degrees is somewhere between 5 and 10. And I'm already below the 150 mark, or I'm sorry, I'm at 158. The next point at 11 is the one that drops below 150 degrees. And then at 15, I'm at 141 degrees. At 18, which is somewhere around here, I'm at 134 degrees. At 22, it looks like it's about 125. At 25 degrees, so right between 28 and 30, I'm at 123 degrees, somewhere right here. At 30, we're at about 116. And I'm just going to keep putting these points on, and you get the drift. I'm basically going to pause this video, and then I'll replay. Okay, so it looks like that I have an exponential curve. So it says what we want to do is graph the data set, and then we'll enter it in our calculator. What I'd like to do first is, again, just kind of draw a curve through this so that you understand that it's exponential. And it looks like it's going to keep kind of tapering off until it gets to a certain temperature. Notice that if you just put a cup of coffee on a table, it's not going to go down to 0 degrees unless you're sitting in a room that's 0 degrees. So eventually it's just going to taper off into whatever your room temperature is going to be. And that's what we'll be able to calculate using your graphing calculator. So what I want to do is have you put your data in your graphing calculator so you can pause the video and enter it all in. And once you do, hit play. And then you'll go to stat. You're going to go over to calculate, and we're going to go down to exponential regression. L1, L2, make sure you have those. I'm going to calculate, and I have an A value and a B value. So it's always y equals, and it's A times B to the x power. And I'm going to round to the nearest tenth on those, and then I'll do 3 decimal spots on the R value. So I'm going to say y equals 171.5. And then we'll do x, or I'm sorry, not x, we'll do 175 as my A value, times the other value that we had of 0.988. I'll do that on my equation, 0.988 raised to the x power. So that's going to represent our equation. And then what I'm going to do is calculate the R value. So it looks like I need to turn the diagnostic on my calculator. If you don't have a diagnostic on, you would go second in catalog. And let me see if this works by hitting alpha and D. I guess not. So I'm going to scroll down. Again, this is only because I do not have my R value popping up. And I'm too lazy to push pause on a video apparently. So I'm going to go to diagnostic on. And I'm going to redo my linear regression, or exponential regression. So I get an R value, and since it's a negative correlation, the temperature was dropping, notice R is a negative number. I'm going to go 3 decimal spots, so negative 0.985, which is a great regression. It's well above 0.9. We're at 0.98. So it's going to be really good for making predictions. So it says, what is the predicted starting temperature of coffee? So what that means is if you were to put 0 into your equation, which if you try substituting 0 into your equation, you're going to end up with the A value. So your predicted starting temperature is 171.5 degrees. According to the equation, it's different from our actual value, which is where my cursor is, but according to our equation, which is something that probably looks like my line, it's at 171.5 degrees. And then we'll just kind of extend this to if a room is 72 degrees, when will the coffee reach room temperature? So I'm giving you a Y value, I'm giving you a temperature. So what I'm going to do is go in to my calculator into Y equals, and I'm going to put in my equation 171.5 times 0.988 raised to the x power. And in for Y2, I'm going to put in when will my temperature reach 72, so I'll put 72 in. And I need to make sure that my plot is turned on, so to make sure of that, we're going to hit second and Y equals, and I'm going to turn my plot on, and then I'm going to hit window. And we're going to start from 0, meaning time, and I'm going to go all the way up to about 100 minutes. So that would be just past an hour and a half, because remember our time was measured in minutes. I'm going to count by 5s, just like we did on our graph. My Y minimum, I'm going to go as low as 50 degrees. And I would like my Y maximum to be 180 degrees. So I'm going above our maximum data point, and I can count that by 20 just like we did. And when I have all that information in, I'm going to hit graph. And notice we have a smooth curve that's coming down to our graph. And again, it looks like the temperature is getting insanely low down there after a while, but then this horizontal line comes across the screen, which represents that value of 72 degrees that we put in. So we're really trying to find this intersection point. And in order to do that, I'm going to hit second and trace, and we're going to go down to the 5th option, which is intersect. And it wants you to select the first curve, which is the actual curve. When it says second curve, we're talking about the horizontal line. And it wants to know the intersection of these two and for you to make a guess. So I'm going to hit enter over this, and it looks like it's 71.9 minutes. So that comes very close to the actual temperature. So 71.9 minutes it would take for the coffee to cool down to room temperature. So according to our exponential graph, according to that function that we had, the predicted function, it would take 71.9 minutes for the coffee to cool down. So it's just over an hour basically in order for that coffee cup to cool. As far as work that you will need to hand in, if you are watching this on the day when I have a substitute on May 8th, you will need to hand in this last problem for sure, along with the backside of that homework sheet from last class. So just this one problem, plus you need to finish the back of the homework. I do not need the first 2 problems from this video, just this one and then the homework sheet.